我们现在是在直播中是吧？
啊，对对对，是的，已经开始了。
哦，对，好，
嗯，
Hi everyone. Welcome to AsiaGraphics webinar. This time should be the first webinar this year in 2026. I'm Yi from Shanghai University, and I will be the host of today's webinar. This time, we are honored to have two speakers, Professor Xihui Liu and Professor Haran Xie, to give their talks. And during the talks, if you have any questions or problems, you can just post them to via Bilibili or YouTube. We will see the questions and we will forward them to our speakers. Okay, now let's begin. The first talk, the title is Interactive and Multimodal Visual Generation Towards Word Models. Our first speaker is Professor Xihui Liu. Okay, and let me give a short introduction. Professor Xihui Liu is an assistant professor at the University of Hong Kong. Her research interests include computer vision, deep learning, generative models, and multimodal AI. She was awarded Stanford World's Top 2% Scientist 2025 and the WAIC Rising Stars Award 2022. Rising Stars in EECS 2021 and Adobe Research Fellowship 2020 for her excellent research works. Okay, now let's welcome Professor Liu to give the talk. Stop my screen.
Okay, can you see the screen?
Yes.
Oh, okay. Thank you for the nice introduction. Today I'm very honored to talk about our recent work in interactive and multimodal visual generation towards word models. This will include a series of our group's recent works in in visual generation. So I'm sure at this time stage we are not it is not new to us that generative models has achieved such great success in visual content generation, including we have seen awesome text to image generation and text to video generation models. However, we are also considering, as a researcher in academia, we are also considering what's the next for visual generation. Are we already satisfied with this text to image or text to video generation, or are there any new possibilities or explorations that we should make in visual generation? So one of these direction is we think the current mainstream paradigm of visual generation is basically passive generation. For example, the user gives a text prompt to the model, and then the model is required to generate a video clip just at once. However, the user cannot interact with the generation process. So we think one future trend should be from passive viewing to active interacting with the generative model, so that not only we can give text prompts, but also we can use our actions or even multimodal conditions to control the generation process and to timely interact with the generative model as the video is generated. Um, on the other hand, our current video generation models are mostly focused on generating short video clips. However, we think in order to push it to reality and to more realistic applications, we need to consider very long and consistent video streams. For example, here's the video I got from Genie 3, and it shows a new paradigm that the user may in real time interact with the generated videos. For example, if there is a door, then the user can control that he or she wants to walk into the door, and there will be a new world inside the door. So with this type of world models, users will be able to create any customized environment and interact with the scene. And also, this type of applications also shed light on the future robotics and embodied AI, because if we can have such generated environments that can interact with robots or agents, then we can enable robots or agents to learn skills in this endless virtual world, just like what we have done previously with the simulation environments. So this type of model, we call it video world models. We are interested in how to turn our current generation technologies into this interactive and even multimodal interactive world models. So in last year, our group did a survey and position paper on this topic. So in this survey work, we systematically reorganize the development of world models and analyze what capabilities are required in future world models. For world models, firstly, we look at the interaction interface between the world models on the right and the real world on the left. So for the real world, we want to interact with world model by our users or designers, artists, or even agents and robots. So these are all the agents in real world that want to interact with the world model. And on the right-hand side, this is the world model. So world model can have many formulations, but in this talk, we will focus on one specific type of world model, which is video generation model as world models. So the left-hand side is the whole world model empowered by the video generation techniques. And for the interaction interface, in the real world, the users or agents or robots can input either actions or text instructions or even visual instructions into the world model. And then the world model is required to generate the future videos in response to the user actions. So what capabilities are needed for this type of video world models? So we think firstly, there are some basic capabilities of video generation models that are essential. We need the generation to be streaming because we need to intersect the user action controls into the generation process. So it has to be a streaming generation process. And also, in order to interact with the user actions in real time, we need the generation itself to be real time. And also, we want the generation to be multimodal because, on the one hand, the interface between the real world and world model are natively multimodal. So we want to control the world model with actions, instructions, or visual inputs. This is natively multimodal. And on the other hand, we want the world model to reflect what the real world is actually, how the real world is actually working. In recent development of large models, this type of common sense knowledge or reasoning capabilities is often empowered by the large language models or large multimodal models. So we think the multimodal capabilities are also very essential for video generation or video world models to develop this type of reasoning capabilities or real world common sense. So what's next? We think apart from these basic capabilities of generative model, there are also four essential components in order to turn a video generation model into a video world model. So the first one is the control. So previously in video generation model, we are more focused on the text control, which is generating videos controlled by text prompts. But on the other hand, we are also for word models, it is also important to control the model with actions. And these actions can provide either navigation signals or interaction signals to the word models. The second part is about physical laws. So the real world is natively very dynamic, and we need to model the real dynamics in word models. So this requires the model to observe the physical laws in real world. The third part is memory, because in order to in order to make the user interact with the word model for a long time, for example, if the user is playing a video game, he or she may interact with the game for hours. So this require very high capability in memory, either the static memory focusing on memorizing the previous scenes, or dynamic memory that's not only memorizing the scene, but also memorizing the status, the most recent status of the scene and the dynamic status of the scene. And the final part is a more high-level capability, which is the intelligence. And we think in the recent language models, we have seen a lot of evidence on emerging intelligence, such as reasoning capabilities or even self-evolution. But in video generation models, these are really explored. So in order to build future word models, the reasoning capabilities and the self-evolution capabilities are also very essential. So in this talk, we will focus on this blueprint, and we will introduce a series of our recent works trying to address some part of this blueprint. So firstly, we will introduce our work on generalizable action control for video generation. And then we will study how to enable the consistent scene memory for very long video generation or very long word models. We will also talk a little bit about multimodal models with reasoning capabilities and also the autoregressive paradigm for interactive word models. So let's start from the first part. So back to 2024, at that time, we see some initial works trying to use video generation models to overfit specific video games. And this provides a lot of inspiration to the community that because this is the first time that we show that video generation actually has the potential to replace the future game engines. But of course, there is still a long way to go. So the question we ask is, previous works mainly focus on replicating existing games. However, we are interested in building new games with the generative models. So the key is how to achieve generalizable action control in these open domain scenarios rather than the closed domain games where we trained on. So in this work called Game Factory, we attempt to leverage the generation priors of pre-trained video models, which enables us to have the generalization capability and a very small amount of labeled game data to achieve generalizable action control, not only working on the training domain, but also can be generalized to pre-train to any videos. So a straightforward thought is because the pre-trained video generation model has shown very good capabilities in generating open domain videos. However, they lack the controllability for precise action controls. So why not we just inject the action control into these pre-trained video generation models and then enable it to generalize to action-controlled results in any video domains. This blue part shows the pre-trained video generation model, and this green part shows the Minecraft data to train an extra action control module to plug into the pre-trained video generation model. And ideally, if we plug the action control model trained on Minecraft, then we can have the pre-trained video generation model to generalize to action-controlled open domain videos. However, this straightforward way does not work well. And we found that the key problem is that after we train this green part of action control, it not only fits the action control capability of Minecraft data, but also it overfits the style information or domain information of Minecraft. So although this blue part is able to generate open domain videos, the pre-trained model is able to generate open domain videos, but after training this action control model, it degrades to only generating videos in the Minecraft domain. So the key technical challenge is how to disentangle the action control from the specific style of the training data. For example, we can only get the action control data from specific games, but how can we disentangle the style of this specific game and the action control capability of this data? So in this work, we propose a multi-stage training strategy to do the disentanglement. So basically, we take the pre-trained model on open domain, and then in phase one, we use the Minecraft data and we train a LoRa on top of the pre-trained video generation model to fit the style information of Minecraft. So phase one is using these extra LoRa parameters to fit the style information of Minecraft. After we have this LoRa absorbing the style information from Minecraft, then we can do phase two. In phase two, we inject an extra action control module on top of the pre-trained module. And then we fix the pre-trained parameters as well as the LoRa that we pre-trained in phase one. And we only train the parameters of this action control module. So because in phase one, the style information of Minecraft is already absorbed in this LoRa module. So in phase two, when we train the action control model, we can ensure that the style information is not entangled in training the parameters of action control. And then in phase three, during inference, we remove this LoRa containing the style information on Minecraft, and we only preserve the action control module as well as the pre-trained parameters of video generation. And in this way, we can discard the style information from Minecraft and only preserve the action control capability from Minecraft, as well as the open domain capability of the pre-trained model. So in this way, we can enable generalizable action control. So although we only use a small amount of Minecraft data to fine-tune the model, our model is able to use this type of action control on any general domain videos. So here we show some results. So we can use WASD or other keyboard or mouse actions to control the generated video. However, when doing this work, we found another key problem of the current world models. So in this example, we can see that if we turn the camera to the right and then we turn back to the left, ideally, it is supposed to generate the same scene because we are looking at the same scene that we have generated before. However, the model actually will not memorize what it has generated, and it will only try to generate some new scenes. So this will cause a lot of scene inconsistency, especially for very long interactions. So the issue of scene inconsistency is caused by the lack of memory, and this is a very significant challenge in interactive word models or in long video generation models. So in our next work, we try to address this memory problem, and we study how to preserve a consistent scene memory in long video generation. So let's come back to the basic architecture of video generation. So basically, in video generation, we have a long history context, which is the frames that we have generated before. And then the model is required to generate these green frames, which are the new latest frames. So in diffusion models, typically we use the most recent history as the context information and use it as a condition to generate the new green frames. So the context window is like this. So we look at the previous several yellow frames, and then we generate these green frames. However, because of the limited context window, the model is not able to memorize what it has generated long ago. And this is a cause of the memory problem in current video generation models. So a straightforward thought is, can we use all historical context as memory? However, we easily know that this is impossible because it will result in excessive computational overhead. If, especially if we have a very long historical context, this will be infeasible. It will be infeasible to take all of the history context as condition. So our observation is that not all of the historical context is important for generating the latest frames. And instead, in most scenarios, when we generate the new frames, we only need to refer to some key frames in history. So this motivates us to propose an approach that tries to use a memory retrieval module to retrieve some key history context from a large amount of historical frames. And then we use this key context information as condition to generate the new latest frames. So specifically, we implement this interactive video diffusion model with camera control, which means that at each step, we know the camera pose of the current frame that we are going to generate. And the model conditions on their retrieved historical context to enable autoregressive long video generation. It is built on top of a video diffusion transformer model. So the key question now becomes how to design the memory retrieval module. So actually, memory retrieval module can be implemented in many ways as long as we can pick the keyframe from historical context. But here in this work, we use a most straightforward way because we assume that the word model has user action as input, which means that we know the camera pose of each frame, which are provided by the users. So in this scenario, we can simply take the overlap of the camera of the field of view of context frame and the predictive frame as a signal for picking the keyframes. So specifically, if we want to generate this pink frame, and we have many gray frames which are previously generated, then we can take the camera pose of all of these frames, and then we take the field of view overlap between the pink frame and all other frames. And we found that these two yellow frames actually has larger overlap than with the for their field of view with the pink frame. So they should play a more important role for generating this pink frame. So in practice, we only retain the highly overlapped context frames, and we discard low overlapping or non-low overlapping context frames. So this is the result. On the left, we show the text prompt as well as the user-defined trajectory in word models. And on the right is the generated videos. So we see that sometimes the trajectory may overlap with the original scenes that we have generated. And if the camera moves to generating the original bridge, we can still generate the same one. So our approach shows very strong scene consistency for generating long videos. We cannot work not only in outside scenes but also in indoor scenes, and also it is worth mentioning that our approach is only fine-tuned on a small amount of rendered data with camera pose annotations, but because we use a pre-trained model on the open domain videos, so our model is able to generalize to arbitrary open domain, even though it is not trained on such scenarios. Okay, so now I want to supplement some more discussions on the memory mechanism for video generation. So we see last year there were a series of works exploring memory mechanism for long video generation or word models. And there has been different type of memories. For example, we can reconstruct explicit 3D representation as memory, or we can compress the frames into latent features or into network parameters as memory. And or we can also retrieve the key context frame or the key context tokens as memory. So for these different types of memory, they may work in different types of scenarios. However, the key finding of our approach, we think, is that even without explicit 3D representations, by approximately selecting key context frames as a memory, the video generation model can exhibit strong ability to preserve 3D spatial consistency. And this shows that the pre-trained the prior in the video generation model, especially the 3D prior in the video generation model, may be stronger than we thought. And this also shows a potential of using pure video approaches to have to achieve very high 3D consistency. But in our context as memory, we only use a very straightforward way of memory retrieval, and we think for this part there should be a lot of more advanced approaches and explorations in the future. For example, for our work, context as memory, we use a rule-based retrieval approach. But we think a more elegant way might be selecting the Keaton context frames with an adaptive way. Like we can enable the network to adaptively select the key context frames without the human-defined rules. And also, we would like to explore how to adaptively update the memory for dynamic scenes. We see that in the demos of context as memory, we focus on static scenes. However, in dynamic scenes, the memory will be more complicated because we have to consider how to update the memory, how to update the status of different scenes and objects. And in one of our recent work, we also explore the adaptive memory mechanism, and we will. I think this work will be released recently. Yeah. So these are some of our explorations in achieving the interactive and long consistent word models. And in the next part, I try to very briefly introduce some of our work on multimodal reasoning and the new paradigms for generative models, because we think the multimodal ability is also very essential for future word models, because we want the word models not only to act as a renderer or generator, but also act as a reasoner that can truly understand the rationale or the rules behind the word. So in this direction, we have work last year in unified visual generation and understanding. So in this work, uh, we try to use a unified model to achieve different granularity generation task and as well as visual understanding task with a hierarchical feature representation. And also, um, unified multimodal model has been a hot topic last year, and we want to rethink what's the advantage of this unified multimodal model. So, one thing that we think of is that with these models that unifies visual understanding and visual generation, the visual generation should be benefited from it because we talk about the visual common sense, the common sense knowledge, and the reasoning abilities for generation, and the understanding capabilities of these multimodal models perfectly provides hints on these capabilities for generation. So inspired by this, we propose the generation chain of thought, which tries to uh, implement the chain of thought reasoning for a multimodal generative model. So basically, in this multimodal model, we instead of directly generating images based on text prompt, we enable the model to firstly generate a chain of thought reasoning. For example, to reason what are in the image and where are the locations of each object, what are the relationships of different objects. Or for image editing, we can use the generation chain of thought to analyze what are the steps to edit this image. So with this generation chain of thought reasoning, we can guide the model to generate image better and to generate a better planned image. Um, so in this work, we also release a large-scale data set for supervised fine-tuning of this generation chain of thought capabilities. So basically, in this data set, it contains over 9 million samples, featuring the semantic or spatial reasoning chains for text to image generation and image editing. And we hope this data set will further benefit the community in this direction. And further, we found that if we apply reinforcement learning after the SFT, it will further improve the chain of thought reasoning of the generation. So basically, after training, if we only train with SFT, the reasoning chain might be templated. It will overfit the human-defined templates for reasoning. But after fine-tuning with RL, we see that the template the reasoning chain of thought is much more flexible, and it really captures the key information that is essential for generating the image. Yeah, so finally, I will talk a little bit about a new paradigm for visual generation, which is pure autoregressive generation. So in previous literature or works, the mainstream generative model is diffusion model, and because of the high quality of the generated samples by diffusion model, it has long been dominating the visual generative domain. However, the mainstream generative model for natural language is actually an autoregressive model, which is based on the next token prediction. And we are interested in whether we can also use this autoregressive generation paradigm for future visual generation or future word models. So for autoregressive visual generation, it is easy to integrate with LLMs, and this makes it suitable for a unified architecture for native multimodal modeling. And also, it also natively supports the interleaved image text generation or streaming video generation and interactive generation in the context of word models. However, the current autoregressive visual generation faces the bottleneck in speed and performance. And this is the major reason why autoregressive model hasn't beat diffusion models so far. So if we look into the architecture of autoregressive visual generation, we found that actually the performance bottleneck is mainly caused by the discrete visual tokenizer. So instead of using a continuous visual tokenizer in autoregressive models, we use a discrete visual tokenizer, and this could cause a degradation in the reconstruction and generation quality. And the efficiency bottleneck is mainly caused by the next token prediction paradigm for autoregressive transformer, because each image is tokenized into hundreds of tokens, and if we generate these tokens one by one, it will be very slow. So we also explored a series of work on how to improve the efficiency and performance of autoregressive visual generation models. So for example, for efficiency bottleneck, we try to replace the next token prediction with next few token prediction, which means that in each step, instead of predicting one token, we can predict multiple tokens in parallel, and this can largely improve the efficiency of autoregressive models. So we developed this training-free approach, which can accelerate 2 to 3 times, and also this training-based approach for parallelized autoregressive generation, which can accelerate up to 10 times. For the performance bottleneck, our work is mainly focusing on improving the discrete visual tokenizers. So we had a work on scaling up the discrete visual tokenizer for better reconstruction and generation quality called GigaTalk. And also we try to bridge the continuous and discrete tokens with our recent work Token Bridge. And in this work, we show that if we discretize the visual tokens properly, it can approximate the performance of continuous tokenizers, and this discretization will no longer be a bottleneck. Okay, so for the sake of time, we will not go into the details of this line of work, but if you are interested, you are welcome to, you are welcome to read our papers or discuss with me offline. So yeah, this is my talk, and thank you, and I welcome any questions.
Thank you, Professor Liu. And so far we haven't received any question, and now it gives me the chance to ask my questions.
Sure.
I'm very interested in your work, Game Factory, and I see that in the demo you just showed, it supports some actions like move forward and move backward. I'm wondering whether it can support more types of actions, such as like natural motion actions.
Yeah, that's a good question. Actually, when we did this work and we have thought of this type of actions, I think in short, it is possible to incorporate more actions within the same architecture. But the major challenge is still on the data itself. So because for example in Minecraft uh we can uh we can collect some data on the user interaction like navigation or performing some specific task like more interactive actions. But these interactive actions may need to be further processed or cleaned because it is mixed with the game interface like other bounding boxes after we conduct an action. So that is I think data is still a problem when we did this work. But of course, if we can have better data or cleaner data on the action control, I think this framework is possible to generalize to any type of actions. And we also see some recent works trying to explore more generalized actions.
Okay, so as long as the time allows, so just the same framework, just the same model architecture, it can support more types of actions. It just that the number of action types change.
Yeah, I think so.
Okay, thanks. And another question is about the memory. So after equipped with the memory, what is the size of the scene it can generate?
The size of the scene. You
Yeah.
mean the resolution or
The spatial size.
the spatial size, I see. I think so in our experiments, we basically try to generate this type of like open scenes or outdoor scenes or indoor scenes within one. The indoor scenes is limited to one specific scenario. Like if one limitation is that if we want to go out of this room and enter another room, then our retrieval mechanism may face some difficulties because the FOV overlap will be incorrectly calculated because of the walls. So this is one limitation. But I think if apart from this wall problem or occlusion problem, for other types of scenes, it is able to generate large scenes. And also, what we mentioned about the occlusion problem has been discussed in one of our recent work. In that work, we replaced the role-based retrieval with an adaptive retrieval approach. And in that, with this adaptive retrieval, we are able to resolve the occlusion problem when we encounter multiple rooms.
I see. So I'm wondering, does it introduce some extra burden if the scene becomes larger because you need to save all the frames, right?
Yeah, theoretically there is burden. Like theoretically we cannot extend to arbitrary long videos. Like if we have 1 hour video, then it's impossible to store all of the previous frames in the memory. So still, I think that's a future exploration that we need to do. Yeah.
I see. Thank you. Let me check the questions. We don't have the questions from Bilibili or YouTube. Okay, so I guess we can just stop here.
Okay, thank you.
And thank you for the impressive talk. Perfect，好人谢。 The title is Creative AI for Professional Design Workflows. Professor Haran Xie is an associate professor at Japan Advanced Institute of Science and Technology and Waseda University, where he leads a human-centered AI laboratory. His research interests include interactive computer graphics, generative AI, and its applications as user interfaces for augmenting human intelligence. He has published over 100 papers in international journals and conferences. And let's welcome Professor Xie to give the talk.
Okay, thank you very much. Let me share the screen. Okay, can you see the screen?
Yes.
Okay, thank you very much for introduction. So, my name is Haran Xie from the Japan Advanced Institute of Science and Technology in the Waseda University. It's my honor here to give a talk about our recent thought and recent work about the creative AI for the professional design workflows. So first of all, please let me do some self-introduction. So right now, I'm in two university, that is in Japan. You can see the map of the Japan here. So one is the Tokyo near the ocean, and another one is the in Ishikawa Prefecture. So normally my research interest is in I love sketch, the drawing things, and all creative things. So I don't have some special I should do research on computer graphics or visual learning. I have a very broad research interest in from hardware to software. So our lab will some students do graphics and vision, especially recently we do image and video generations. Also, we do some robotics for hardware. Recently, we have some research funding to support the robotic learning, and especially because we are in Japan, we also consider how to use generative AI for anime, some professional design. Also, we collaborate with other university on about the architecture design, also some archaeology that is for the Oracle bone. That is, I think all these things is very interesting. Especially, I also some interested in fluids. That is for some mathematics things. Yes, that is my research interest. So yes, thank you very much for the invitation to join this webinar. Actually, I'm the one follower of this AsiaGraphics webinar in YouTube. So I contribute one among the 200. So a lot of my respected professors and my friends and collaborators that already give the talk in this webinar. So I really enjoy all the talkers. Especially today's talk is related to this talkers from the Professor Igarashi and Professor Fu, also from my friend Zheyu and Chao. So if you're interested, you can also to check our previous webinar. You can check all these contents on the video. So this is one slide actually I borrowed from the Professor Igarashi. So this is one slide he introduced the human in the loop creative AI. So this is we want to introduce that nowadays we use the AI, especially generative AI, to do content creation. That is for the image, video, and any contents done inside our computer. So we want to use these generative AI tools that make ourselves be creative. So this is a definitely paradigm shift right now for content generation. So this is also all the topics in our labs, especially for image generation, video generation, and used for robotics. So we think or what happens when we have really this kind of powerful generative AI, especially right now we have some video generation, also previous speaker talk about the video models, word models. So this is also one slide I borrowed from the Professor Takeo Igarashi. So this is presented in UISD last year. This is a vision paper. So the title is Easy and Fast. We should rethink the future of the content creation tools. So basically, generative AI, image and video generation make it very easy and faster for everyone to create the contents. You just use one prompt, you can generate an image, you can just one prompt to generate a video. But it is really that is important or the right goal that we achieve for the generative AI. Because for normal people, for everyone, if you just very easily to make something, they will feel very boring. And so, for example, right now, image generation and video generation, if we use it for experts, they maybe think it is not helpful at all. So there are some inconvenience truths about easy and faster. I don't introduce the details here. If you're interested, please to look for the paper and the video from the Professor Igarashi. So this is the answer that beyond the easy and faster from the that paper. So there are three answers here. So we should think about the value in the process and then rethink the purpose of the content creation and then rethink the unique list. Why we want to create something that is special. So especially here, I focus on the value in processes. Why we focus on this is so this is also I borrowed one slide. So true value of the content generation is in process that is not only just the output. I mean the just the pixel of the image or just the video. That is the final result. We need to focus on the how to make such contents, such image or such a video. So for some special reasons, for example, for enjoyment, for people that can do some exploration, for people and people, human can do communication. So that is I mean, for the future, or that is the core part. We should think more about the content creation tools, use generative AI or any other tools. So here my thought is that uh, about the creative AI, that is AI should learn from the people, learn from especially from experts. The AI should know how people to make things, to make image, to make fabrication, to make anything, any contents. Then the AI understands the process. They can help or transform their working flow. So workflow. So this is the main. So we need to study more about the processes. So this is basically the reason our work, our focus on the using creative AI. So here is one paper that is some years ago. So we want to understand the process of the human drawing. So we observed the drawing process. So what is the patterns or when they draw something that is quite beautiful. So we can find that. So when we understand the process, one way is that is to do some explicit guidance. That means, for example, when you draw something, you first have to draw the global. I mean just the whole shape, the outline. Then you draw the local. So this is from the recognition process. I mean, that is special for human to observe things. So we depend on this finding or observation. We can give some guidance to the users that to help them that really can create something by themselves. So, for example, we can give some guidance, user guidance, first from the global. So give some outline features, and then they can draw it. So after that, so this is because this is somehow old paper. We use a gun-based method here, that is use some to generate the faces with the use the masks. So this is for the local guidance, so we want to help the users to draw the details, for example, the mouth and the eyes. So this kind of details, when you draw something, you cannot imagine this. So we also based on some gun. This is based on master gun and AP draw gun, some kind of old. But the idea is that we can give some local guidance. So after that, we really to ask people to try it, to do some user study. We found that these controls can really to help the user that can draw better. Even for some high skill users, they can draw something different. So we can get some answers for from the user experience that they really that can this can process can help the people to draw the things even for diversity different groups. So our another paper is consider about how to make the general model safe to understand the process, the drawing process. For example, for the anime. So the problem here is that actually when we draw something, that is one process of where you draw the face and then draw the eyes. But for the computer that cannot understand the process, the sequence. So we need to make this sequence in the latent space of the generative model to make it collect together. So in that sense, we can if we can do these things. So next time, if the input just some incomplete sketch or incomplete drawing, so we can generate some result that quite completed and perfect result. So basically what we do that is we to disentanglement the feature of the face because this paper is only focused on the face. We do the segmentation for the human drawing. Then this paper is based on Stygon, so the diffusion model right now is not so popular. So we use a Stygon, especially for the structure code and color code to control the drawing, help the drawing process. So there is a one user interface here that user can draw some parts of, for example, for the eyes. Then we can generate the whole image, the whole faces. So then you can to user can verify the result, then give some guidance, just as the background. We call it user guidance, and like a shadow. This is shadow guidance. So in this sense, it can help the user to draw. Even the original drawing is not so perfect, but we can see that when they use this kind of interface, it can really to helpful for the drawing. So compared to the other papers, we can see we do this kind of exploration, so we can get a very clear result that is compared to other papers. So other results. So this even the input is very bad. So this because we care about the processes, even we draw different steps or different result. I think the result also quite the same because we understand the drawing process. So from some very bad input, we also can generate a very cool or cute and like the professional drawing. So we also understanding the process, especially how expert to draw. So when you expert draw something, they use different lines. I mean, different thickness and different like features of the lines, like a shading edge or some global features. Also, when you draw these, first you draw the just the outline, then give the colors and the other lighting conditions. So this is all the human recognizing process. When you do drawing, you never do it inversely. So based on this, this is our collaboration work with Jilin University. So this is work we wanted to recover the image from the just the line drawing of the boson. So we can see that the generated result can get the feature from the reference image. Of course, not only just some browsing, so we can also to generate some fashions image and all the professional design for architecture, for animal, or for industry designs. So basically, the idea is here. So the backbone is quite common. This is API uses some API adapter and control net to combine it together to give some strong control and a weak control. But here the special we add is the input. So we get the input to we divide it into different features of the double edge, single edge, and the soft edge. For reference image, as we said before, we add this to decomposition, the illumination effect. So in this sense, we can get this entangle feature then can generate better. So basically we get the insight from the drawing pair processes, so we can get the features of different edges from the drawing. Also we get the idea from the oil painting, so we can consider different color and illumination effects. So one minor contribution is that we also construct the data set for professional drawing, so that it can be useful to for especially for to understand the how exporters how this kind of work to recover the texture features. So we compare to other methods, basically compared to others, we achieve some good results. Also, here is some metrics with some different qualities and different metrics, especially because this kind of thing is about quite subjective. So we also do user preference study to ask the people how this result look like. So of course we can get we got some result overall quality and appearance perception and edge fidelity we get the best one. So this kind of task is not only just for some uh, quite not fine drawing, I mean professional drawing. It can also for some hand drawing that is quite rough, not so perfect. So we can use it for different scenarios. So until now, so I explained some our previous work is to how to understand the process of the drawing or the design. So we get some from three aspects. So recently, I especially that have some research project that collaborate with the company and the university. We really want to help for that use some generative AI tools that help the exporters. So here in this talk, I only introduce some research result. We collaborate with the Department of Architecture in Tianjin University that we do in last year. We also have some work for animal and or that is a new result from this year. So I will keep it maybe short for just introduce some our previous result. So when we consider about the architecture design, this is a quite something that not just common people can do. They need some professional knowledge. So this is have some actually a real workflow because they need to really build such things that the human view that is very strictly be safe and be in different vision aspect, also in some physical aspect. So this work we basically best for the concept design. So one two-dimensional design. So for the design process, first the architects have some rough sketch, then they give the details, finally give the colors. This is like some drawings, but the process is similar, but we need to consider more about some functions. Also, for the 3D design of the architecture, so basically the process is that we have some white box, they call it shoebox. So we can then add the details of the structures. So finally we get some of the buildings. So this is the process how to do the 3D design. So normally when you use grasshopper or a Rhino, some special, especially professional tools for architecture, this is a very annoying or tedious work. You need to adjust every details of the building for the windows, for the doors, especially when it is quite I mean, some group of buildings for the university or for the shopping mall. I think this can be very tedious. So we think that how the really generative AI can help this work that is in practice. So last year, we published one paper to do the survey about all generative AI that can help for the architecture design. This is we analyzed the gap between the computer science. Right now, computer science have diffusion models, autoregressive models, some video generation, but actually in the area of architecture or architecture design, they just use Rhino, or they even don't use Comfort UI. So they depend on the plugin they use it in Rhino. So actually, the culture gap between two field is very huge. So we want to do some work that just to fill this gap to for the architecture design, this kind of professional design uses state of art, the generative AI models. So here is some examples where you use some image generation for architecture design. For example, the input is three-story building, but you can see that from Stable Diffusion or other models, the result totally different. This is the result maybe fifth or sixth story building. So the image generation is just generation something that looks beautiful, but actually it's functioning not correct. Also, we can see some details that, for example, for the left image, you can see this result looks good, but when we see the details, the result is totally wrong. So the story is different. Also there is no window on some side. So it's not useful for architecture. It's like a toy that for common people. So we want to we thinking about how that we can improve this can text to image generation to help solve this kind of issues to solve this hallucinate that to the training data, also some special relationship and the details that didn't considered in the common generative models. So here is the one of our work is to from the architecture sketch to the concept representation. So the input maybe some rough sketch and some text prompt, but the text prompt with some concrete requirement, for example, three-story building, also with some open entrance area that is the requirement for the architecture design. We want this result can achieve something that is to meet this requirement. So what we do this, so we get as I planned before, we want to understand the process of the design. So we divide the from the first our first observation, we use the implicit guidance that we first to get some rough details, then get the fine details. So from rough sketch, we get the detailed sketch, and then finally we get the rendering result. This so to get to understand the process that may be helpful for the architecture image generation. So basically, the framework is like this. We use the segmentation model and the diffusion models, but basically we use the retrieval augmented generation (RAG). So that is make the result more accurate to solve the elucidate issues. So first we do the segmentation. We use the segment anything to segment all the elements of the input. Then we, from the segmented input, we generate the same style to get the masks. Then we, from the masks, we explore from the dataset to get the correct architecture parts. So we can replace the bad one in the design. So that means we use the sketch-based retrieval that is a famous work in SIGGRAPH 9 years ago. So we compare the features of the input sketch and then the data set, so we can get the retrieved components. So after that, we from each component we generate the suitable component for the detailed sketch. So for component generation, we use some weak conditions. So we use the RP adapter, that is use the attention control for the features. So we use this controller plus the RP adapter, so we can get the generate component. So after that we get this, we do some image mapping to get it back to the architecture sketch. So finally, we use the control net. This is a fine-tuned control net based on the dataset of the actual building dataset. This is we especially choose the university campus that is from the Department of Architecture. So we use this dataset to fine-tune the results, so get the final result of the architecture images. So we built the component dataset, architecture dataset of different windows and doors because there's some patterns of this kind of parts, the components. So we use the training set, the dataset from the actual the building cases. So we use the we especially focus on the university campus like here. So we get this kind of result. So from the course sketch, we mean without too many details. First, we get some retrieved details, then we combine them together. So finally, we get a more accurate result. So some updation study here that combine compared to the some text to image generation models. Basically, we get a more accurate result. So another work I want to show is that from abstract representation to architecture, the 3D models. So how to get the 3D models? Here we mean the multi-view image of the buildings. So from the shoebox, just a very simple 3D model. So this is the basic the task for architecture design. So we want to understand the process, especially expert knowledge when they design these kind of 3D models. So here is the one concept is level of details. So they have the level of details. So for LD1, level of details 1. So there isn't any component like windows and the doors. So then we add some details of the different parts. Finally, we also add some functional part, also add some texture. So finally, we get the 3D model. So there are different level of details from the, also the 3D structure. Also, we can say this is the sketch dataset, the drawing. So we propose one framework that is to generate a multi-view consistency the image generation. We should note that this work didn't use level of details, but recently we have new work to focus on that. So basically, we first to use the step diffusion to generate different target images. So we use different losses, so style loss of the images and the structure and the orientations. So then we, as a one condition, we also use the depth map. So we use the meters, that is most famous model for the depth generation. Then for the multi-view fusions, we use the MVD fusions that to generate different view images. So for the training dataset, we use the architecture 3D models, that is professional models. So we get the models with the pale data of the shoebox, just a simple 3D model, and then the final result. Basically, we use the over 200 architecture models. So from this, we can, from different input, that is even a very simple input of some just a box, we can get the details of the generated architecture 3D models that in multi-view, different viewpoint that be consistency. So to evaluate such a result, we ask some expert users that is from the Department of Architecture. So do some user preference studies about the structure integrity and structure inconsistency. Basically, we get somehow good results. So in future work of this, we want to incorporate more diverse and realistic input data for real world building design. For example, for this kind of very busy buildings or some quite for the shopping mall or some more with some actual uses. So we also want to improve the fine-grained control of the input image. So that means we can control different layers, different stories of the buildings. So we even can control the lightings, also, for example, balconies or windows for this kind of buildings. So here is a simple conclusion. So our work, recent work to consider about use creative AI, generative AI to understand, also want to transform a professional design workflow. So for this purpose, so we need to really understand the processes of the workflow. So how people, how expert, especially skilled people, how they really do this kind of things. So we understand, we try to observe them and then to understand some patterns. We want the generative model to can learning the processes from the different features. So then we get based on the understanding of the process, we can transform the processes to that can use for different professional design. I mean, professional design that is also can help for common user, but we more focus on how to really to help the expert user to get the high quality results. So here is the one from the previous slide from the Professor Igarashi. So true value of the content creation is in the process, not only just the output of the pixels or sequence of the pixels, like videos. So we want AI to understand the human, and the human can give some feedback to the AI, so that can improve the human AI coexisting. So creative AI or generative AI is not just a tool that help people. I think that the generative AI or creative AI is a mirror. So from the mirror, the people can understand themselves, can understand what can make them more powerful, what can augment their capability to make them that be stronger, that not just the AI can replace the humans, replace the designers. So I great thanks to all my collaborators and most student and lab members that contributed to these workers. So yes, this is all from my talk, and welcome to join our lab if you apply the master and the PhD and the research assistant or internship. Yeah, that's all. Thank you very much.
Thank you, Professor Xie. And yeah, I have a question about the architecture design. I see that in your method, the input is a complete sketch or a complete shoebox. But because I am a very non-professional user, so maybe I don't have a clear idea in my mind, like what I want to create. And I sometimes I find it is practical to have an interactive system that the AI can talk with me, he can teach me how to think, and it helps me to form a clear idea, like which kind of this architecture should look like. Uh, so I want to ask you that, in your opinion, do you think this kind of interactive system is just system development work, or is there some technical challenges here to develop such interactive systems?
Yes, thank you very much for your question. This is very important. So when we do all these works, this is one core things as you ask it, what is the design intention? What is really the user wanted? For the common user, they maybe just have some rough idea. They just want to, for example, I want to build a house. They don't have concrete idea. This is for the common user. But for the expert, they're totally different. They already have some idea. They already have experience. So in that sense, maybe they don't want just interact systems. They want something that can really helpful for them. So that means for different level of user or different purpose from the user, they have different design intentions. So as you said, that what we can do that make some technical contribution from this kind of interactive systems. So I want to say that right now, generative AI is all about the data, all about some video data, image data, or text data, but that is not human side. What we really don't understand is about human self. When we give an input to the human, we can get the output. So this is the black box here, but we want to the design the intention here. So we want to make the view human more differentiable or more recognizable. So we can make a totally new framework that can recognize this kind of process. I think this is quite important, especially when we as a human, we should understand ourselves, and then we use some computation models to solve this problem. It's not just something that is very easy to solve, like use some data or images. Yeah, that is my answer. Maybe.
Yeah.
Yes, thank you very
Thank you.
much.
Yeah, it must be fun to work on such creative AI and the co-creation of human and AI systems.
Yes, thank you.
And we have received one question from Bilibili. The question is about the last method to generate architectures. Yeah, the question is that does it support more fine-grained details, like the details of the window? Does it control such kind of details?
Yes, thank you very much. So right now, this work is quite our first step to do this. As I explained here, so we have different level of details. Right now, we just do the first step or use just some shoebox. We cannot control the window or the parts explicitly. So, but in future, we want to give more control. We want to define different level of the details of the design. I mean, this sketch. So in that sense, we can solve the problem, how, for example, to design the window or design the door or design any element for that. So this is also the process when the people do the design. They do it procedurally. They basically add the details when they finish the previous steps. So yeah, so also this is our future work, I can say. So we will work hard maybe this year to want to make some result. Yes, thank you very much.
And the next question is, some works employ segmentation models for semantic analysis, while others do not. In what scenarios is segmentation knowledge necessary, and what are the underlying reasons for its necessity?
Yes, thank you very much for these questions. I think, yes, some work with the segment anything here. So, basically, when we use the segment anything, actually they cannot work very well for the architecture images because there are many elements there. For example, windows, there are many windows there. For segment anything, they just get a mask of some area, but it's not correct at all. For example, this is the first work we want to do the retrieval augment generation. So we only focus on the window and the door. So we use the segment anything, use segment here. But in future, I think segment anything cannot work here. We need to propose a new segmentation model, so especially for this kind of fine detail image, for the building images. Also, there are some overlap, right? For example, here there are some tree behind the tree. There's a door. So this is quite complex to do these things, but we want to impose this kind of segmentation workers. Yes, that's the answer. Thank you.
Thank you. And okay, so we have perhaps it's the last question. Is there a way to make a sketch to represent 3D objects, like allowing on multi-angle sketches?
Yeah, that is a very good question. So everyone knows that sketch is in two dimension, especially when we do the sketch that is on the screen. Recently, there are some work they use the virtual reality, VR or augmented reality. They can draw it with 3D input, 3D trajectory input. So they can draw some multi-angle sketches. This is one possible way. Another possible way is that when we do some in 2D screen, we just give it another dimension. I mean, for example, the Z dimension, we can control the angle. So we also can do some multi-angle sketch. But of course, that is not the intuitive way to do this. Most intuitive way is to draw in 3D spaces. But that is a good question because from two dimensions, how we can know the depth from this sketch, how can we know some overlap of the sketch? This is still we have some we can do a lot of work to improve this. Yes, thank you for the question. That is my answers.
But it might be challenging to ensure the consistency between these multi-view sketches.
Of course,
So perhaps it's straightforward to use some 3D representations like wireframes.
Yes, but wireframe don't have some details, right? Just the outline. Or if you consider about some like details of windows, basically there is definitely some solutions to solve this, like wireframe, and then use some hybrid representations with some 3D presentation and some 2D images. I'm not sure, so definitely there is some solution to solve this. But it is very challenging, as you say.
Yeah.
Yes.
Yeah. Okay, so we have dealt with all the questions. Okay.
Okay,
So
thank you
thank
very
you,
much.
Professor Xie, for this talk.
Thank you very much.
And now it's the end of today's webinar, and we thank our speakers for your interesting and an excellent talks, and we thank the audience for your time and for attending this seminar. Okay, and this is the end. And 我们现在是结束了是吧？
对对，我已经结束直播了。对。
哦，行行行，好。